So these are some sample example problems on electrostatics, Coulomb's law, and electric field. So I choose mostly from my lecture slide. That will help you in doing the assignment. So the first problem is really simple. So here you have three charges, Q1, Q2, and Q3, and these are the magnitudes lying. These are all static charges. That means they are not moving, lying along the x-axis, and these are the magnitudes. So Q1 and Q2 are positive charges, while Q3 is negative charges, and their magnitudes are given in microcoulombs. So and the distances between these two charges are also given. So it's acting using the vector superposition principle. It's acting. What's the net force, net electrostatic force acting on charge Q1? So we're calculating the net electrostatic force or electrical force on Q1 due to the presence of Q2 and Q3. Or it may ask you what's the net force on Q2, or it may ask you what's the net force on Q3. But in this particular problem, as an example, it's just asking what's the net electrostatic force acting on Q1 due to these two charges. So here's the free body diagram. First of all, vector free body diagram. All right. So this is the charge. So you're drawing the free body diagram, right, for Q1, and this is the force due to 2. So we call it F12. And what's the magnitude? F12 magnitude, right, is given by Coulomb's law, and is K Q1 Q2 divided by R12 square, right? So this is given by Coulomb's law. So K, the product of the magnitude of the charges divided by the square of the distance. So let's put on the K is a big number. It's an electrostatic Coulomb's constant. So I use approximately 9 to the power 9 for simplicity. So you just need the magnitudes here. So Q1 is 10 microcoulombs. So 10, make sure to convert into coulombs, negative 6 times Q2 is 12 microcoulombs. 12 negative 6. Remember, you just need the magnitudes here, even if it is negative charge, because Coulomb's law only calculates the magnitude. You have to figure out the direction. And R12, which is the distance between Q1 and Q2, it says 100 centimeter. 100 centimeter is 1 meter, right, square. So that's the magnitude of the force 1 by 2, right? This is the force on 1 due to charge number 2, right? This is exactly like this. And if you do that, so what you're going to 1.08 newtons, right? So that's this. And it feels the charge Q1 feels force of repulsion, because this is positive, this is also positive. So force Q1 feels force of repulsion, right, from Q2. Now do the same thing with the Q3. So what's the force on Q1 due to Q3? And it feels force of attraction. So we call it F13. And let's calculate the magnitude again using the same formula. So you want Q1 Q3 divided by R, distance between 1 and 3 square. And again, same thing, so Q1 is magnitude 10 to the negative 6. The magnitude of the Q3, remember, even if it is negative charge, you just need the magnitude in Coulomb's law, and divided by the distance between, it says the distance between 1 and 3 charge is 3/4 of R, and R is 1 meter, 100 centimeter. So that means it's 75 centimeters, 0.75 meter, right? So that's your F13 magnitude. If you do that, 2.56 Newton. But now, since we have calculated the individual forces, now what would be the net force? Since they are lying along the same axis, so it would be really easy, right? Because the net force will be that direction, because this is bigger, right? So the net force will be this stronger force minus this force. So the net force magnitude will be the F13, which is stronger, minus F12, right? And this is 2.56 minus 1.08. So the net force acting on charge Q1 due to the presence of Q2 and Q3 is this. So it's 1.48. So what's the direction? To the right. So its direction is to the right, because this is stronger. So that's how you solve. Now still Coulomb's law, but slightly different. Now the charges are scattered in two dimension laterally instead of just along single x-axis. Now Q3 charge has moved laterally. Same distance, 3/4 of r, right? 3/4 of 100 centimeter, but it's separated laterally now. It's making 60-degree angle. So what's the now is still acting? What's the force on Q1? The net force on Q1, right? Now this is your new free body diagram. So first of all, again do one at a time. So what's the force of repulsion felt by Q1 due to Q2? This, right? And what's the force of attraction felt by Q1 due to Q3? Now this will be in this direction. This will be 1, 3, right? Because this Q1 gets attracted towards Q3, because Q3 is negative charge. And then now back to the vector problem, right? So if an object is acted upon by two forces like this, how do you calculate the net resultant force? Then you will do some vector rules. So calculate first. Your first job is to find the magnitudes again, right? So K, Q1, Q2 magnitude divided by R12, and this is going to be same because the numbers, actually the magnitude hasn't changed, actually only the direction has changed. The individual magnitudes is same because they are separated by same 1 meter distance. The magnitudes are same. So if you from the first problem is 1.0 Newton. Similarly, the magnitude of this, right, this F13, which is the force felt by the charge number Q1 due to Q3, is K Q1 Q3 R13 square. So, and again exactly same numbers, put everything same, 2.56 newtons. Now the problem is to find the net force here, right? You can't just subtract these two, because why? Because see, these vectors are not lying along the same line. So then how do you find the direction? So then go back to the picture. So it will have two components, right? This will, because since it is angled based on the vector rule, first you have to calculate the x and y components. So the x component will be F13 cos 60 degree, because it's 60 degree, and the y component will be y component, right? Let's say it will be F13 sin 60 degree, and you have to take into this account. So what's the vector rule? So the vector rule says first you have to find the net force in x direction, which is now F13 cos 60 degree minus F12. Why? Because this is acting in opposite direction to this x component, right? So put the values. F13 magnitude is 2.56 cos of 60 degree minus F12 is 1.08. So the sum of the x component of the force is, you do that, 0.2 newtons. So similarly, you have to find the sum of the force in y direction, and in y direction you have only one force, only one component, which is F13 sin 60 degree, and which is positive, right? Because it's in first quadrant. Both components are positive. Okay, so put that. F13 is 2.56 but sine of 60 degree, and if you do that using your scientific calculator, so that's gonna be 2.22. Okay, so now we got the sum of the y component, sum of the x component. So how do you find the net? Because what we simply did is we have split it. We have decomposed all the forces into x and y component. So this is the sum of the x, right? This is just a vector review, sum of the y. So then the resultant is just given by this parallelogram method. Just build a parallelogram, right? And this is the net force, and this is the net resultant angle. So then that's what we do. So then the net force is given by, the magnitude is given by just the square Pythagorean, right? Because this is given by this square plus that square. So the sum of the x component square plus sum of the x component y square, and we have all the numbers, right? And 0.2 no, I just put like this, square root, that's fine. So the net force is almost same as xy component, so it's 2.23 newtons. So that's the net force, electrostatic force acting on charge q1, right? And what's the direction? Because we have to find the direction as well, because force is a vector quantity. So the direction of the angle made by this resultant force with the x-axis is given by, if you just see the geometry, it's gonna be inverse tan sum of the y component divided by sum of the x component. I have the vector rule. So y component is 2.22 divided by 0.2, right? So theta r is 85, about 85 degree. So you also need to mention the quadrant. So this is because both components, see, some of the x is positive, some of the y is positive. So that means it's in the first quadrant. You must mention this in the first quadrant. Okay, so that's your answer. This is your answer. Here's the important, techniques or recipe to solve the electric field due to a point charge or system of charges, at a given point. So this is how you solve the electric field problem. So first, for the given problem, first you must draw, the free body diagram. You must draw the electric field due to individual charges. Then calculate the magnitude, magnitude of the electric field due to individual charges just by using this formula. And then find the x and y components of the electric field produced by the individual charges, right? And then find the sum of the electric field in x direction and sum of the electric field in y direction. After that, you are pretty much done. The net electric field is then given by square root of the sum of the x square plus sum of the field in y square, right? Square root. And since electric field is a vector, so this just calculates the magnitude. So the direction is given by then this, right? Inverse tan y component, sum of y component and sum of x component, and also mention the quadrant, which quadrant it lies. That's all. So the next problem is calculating the net electric field due to various charge distribution, and make sure to first read the instruction on how to solve the net electric field problem instructed in the previous lecture slide. So here's the problem. So first one is really easy, just to understand electric field concept. So here you have a positive charge whose magnitude is 0.1 microcoulomb, and it's just asking what would be the net electric field produced by this charge at point P. Point P is, remember, it's an empty space, right? At 10 centimeter distance, and based on the rule, since this is a positive charge, the direction of the electric field we know is away from the charge. For a positive, remember, if it is a positive charge, the electric field, the direction of the electric field for a positive charge is radially away, and if the direction of the electric field due to a negative charge is radially inward, right? Because our test charge concept is positive test charge. So based on that, so it's asking what's the magnitude and direction of the net electric field produced by this at 10 centimeter distance at point P, right? And that's really pretty easy. So just use the since you have only one charge, you don't need to do any vector addition. So the magnitude of net electric field is just given by the formula K, the magnitude of the charge, which is this, divided by the square of the distance. That's it. So K is again same K, 10 to the power 9, right? And the magnitude of the charge is, it's a 0.1 micro, so 10 to the power negative 6, divided by square of the distance. So distance must be in meters, remember. 0.1 square. So that's the net electric field, right, at point P. And if you do that calculation, so it's going to be 9.0 10 to the power 4, 90,000 newtons per coulomb at point P. And what's the direction? Direction would be to the right. right, as shown. Because why? Because it's a positive charge. Net electron, net field, electric field due to a positive charge will be radially outward. So at point P, this direction. Now still this is number 3 problem, part B. So number 3 part B says now, so this was number 3 part A, right? Now in addition to this positive 0.1, you now put one more 0.1 positive microcoulomb charge at 10 centimeter distance laterally right here. Now it's asking what's the new net electric field. Definitely this charge distribution will change the net electric field at point P. Now it's asking what would be the net electric field now here, right, at the same point. Now first the rule is first you need to draw the electric vector, because let's say this is charge number 1, let's say this is charge number 2. So at point P, right, what will be the electric field produced by 1? Since this is positive charge, is away from the charge. Let's say this is E1, right? And what's the electric field due to charge number 2 at the same point? So well, you need this lateral distance, you need this diagonal distance, and at point P the electric field produced by this charge number 2, which is also positive, is away like this, right? So let's call E2. So first you're going to need this E1 and E2 magnitudes. That's your first job. So, and it's given by just the formula by R1 square, and that's the same actually, 9 to the power 9, and Q1 is 0.1 to the power negative 6 divided by 10 centimeters, so 0.1, so it's 90,000. That's from part A, right? So now what about E2? The magnitude of the electric field E2 due to the charge number 2. Now you need this distance to calculate E2. You need this distance, right? Because this is the distance of point P from charge number 2. And if you do this, 10 square plus 10 square root is about 14.1 centimeter. So then do the same thing, K Q2 divided by R2 distance, right? So 9 to the power 9. Q2 magnitude is 0.1, charge is same. Now distance is different. Distance you are going to need 14.1, so which is 0.141 meters, because remember you need meters. So that's the magnitude of electric field E2, and if you do that, is 4526 9 newtons per coulomb. So that's the magnitude of the. Now since this you have two electric field vectors, electric fields are vectors, you have two electric field vectors acting at a point. So then to find the net electric field, then you have to do the exactly same vector addition that we did before. So first, since this is angle, right, so I'm gonna magnify that. So point P is right here, so this is your E1, we have just calculated. This is your E2. Remember E2, no, E1 must be bigger actually. Let's make it a little bigger, because E1 here is 90,000, which is E2 is less than that. So this is your E1, this is your E2. Now since this is 10 by 10, right, so it must be 45. If not, then you will have to find this angle first from trigonometry. So if this is 45, this is also 45, so this angle is 45 degrees. So first, since this E2 is angle, you have to find the components actually, right? So x component is, this x component is E2 cos 45. The y component is E2 sin 45. Make sure you split, you decompose everything into x and y component. Then do the regular vector. So then first you need to find, before you find the net electric field, you first need the sum of the electric field in x direction, right? In x direction, what's the sum? So both this E2 cos 45 plus, because why? Because it's in the same direction, plus E1, and put the number. E2 magnitude is this 45,269 cos 45. E1 is 90,000, right? And that's it. That's the sum of the electric field in x direction, right? And calculate that, and that's going to be 1.22 10 to the power fifth newtons per coulomb. So similarly, you need the sum of the electric field in y direction. So sum of the electric field in y direction has only one component. This is contributed from this, but this is in fourth quadrant, right? So it is negative because it's facing down. So make sure you put negative E2 sine 45. That's it. If you have other y components, so some plus and minus, but since you have only one, so this is now E2 is 45 269 sine of 45 degree. So sum of the electric field in y direction will be, so if you do this calculation, so it's going to give you negative 32010 newtons per coulomb. Now once you have the sum of the x component and sum of the y component, you are almost done. So the net electric field magnitude based on our rule is this, right? Squared from Pythagorean theorem. And put this and this square, and then that's going to get you 1.26 10 to the power fifth newtons per coulomb. But that's not completed yet, because we also need to find this direction, because we know is, so let me again draw this here. So this is because E1 and E2, we know that the net electric field from parallelogram method, right, will be this direction. This is the magnitude of net electric field that we just found. This. But what's the direction? We need to figure out this direction, the angle made by the net electric field with the x-axis. So theta r is the angle made by the net electric field with the x-axis. Will be inverse tan y component, remember, always y component divided by x component. So if you put that, just put the magnitude here. So 32010 divided by x component is 1.22 10 to the power fifth, and if you do that, it's going to be 14.7 degree. But you have to mention the quadrant. So this net electric field here is in fourth quadrant. See here, fourth quadrant, first, second, third, fourth. In the fourth quadrant. So you have to mention that. So this is the net electric field, right? This is the net electric field at point P due to these both charges at 14.7 degrees. Now this is still problem number 3, but this is the last part C. Now it says for part number B, remember you have two positive charges separated by some distance, and at point P we have calculated the net electric field, and that was in this direction from part B, if you remember, and that's the net electric field, right? And that was calculated as 1.26 10 to the power fifth newtons per coulomb. Now it says part C says, now if you place a small test charge, 10 positive 10 nanocoulomb charge at point P, what would be the acceleration produced on this? Because if you put a charged particle in electric field, the electric field exerts force on the test charge, and the test charge will accelerate, right? That's the main idea. And since this is the test charge is this test charge, the small test charge, is positive charge, it would accelerate in the same direction as net electric field. So how do you find the electric field? So the acceleration is from Newton's second law, net force divided by mass. Mass of this test charge is given. So, but how do you find the net force on this test charge? So then just use QE net, right? That's the formula for in terms of electric field. If you know the electric field at given point, the force on the test charge will be just Q times E, right? Divided by mass. And Q is the test charge now, right? This Q is the, because we're finding the acceleration on this test charge, that this is the Q is 10 nanocoulomb. Nano means -9. And the net electric field we have calculated from 3B is 26 10 to the power fifth, And mass of this test charge, 10 nanocoulomb test charge, is given 6.67 10 to the power negative 23 kilogram. So the acceleration produced, right, will be huge actually. So if you do this calculation, so it's 1.9 10 to the power 19 meter per second. And it's not surprising because this test charge is very tiny, its mass is really small, so acceleration would be really big. And since again acceleration is also a vector quantity, what's the direction of this acceleration? In the same direction as the net electric field. Why? Because it's a positive charge. If it is a negative charge, then it would accelerate in that direction, opposite to the net electric field. Since it is a positive charge, its direction is in the same direction as E net. Okay, so that's how you solve this basic problem. Here's the next problem. So here's you have two charges, both positive charges. One is 40 microcoulomb, the other is positive 20 microcoulomb. They are separated by 30 centimeter distance. It's asking between these two charges, find a point where net electric field is zero, right? So first let's assume that this is the point, let's say point P, where the net electric field is zero. So why there is a chance that the net electric field is zero? And because of the cancellation of the electric field. Let's say this is charge number 1, charge number 2. What's the electric field at point P due to charge number 1? Because this is positive, again this is away, right? This is E1. And what's the electric field due to charge number 2 at the same point? That. So at that point, right, we assume that the two individual electric field cancel each other, right, like that, and the net electric field here will be 0. That's the main point, right? And it's acting at what point? So you have to measure the distance, actual distance. Let's say we measure distance from reference, keep this as charge number 1 as reference. So let's say, since we don't know that distance, let's say this particular point P is at distance x from charge number 1. And if this is x, the rest of the distance, this will be 30 minus x, right? So 0.3, because 30 is 0.3 meter minus x. So the main idea is, right, at point P, the magnitude, right, must be equal, right? That's because they are equal and opposite, right? The magnitudes must be equal and opposite direction. So that's how. So then E1 magnitude, so K Q1 magnitude divided by R1 distance, right, which is x, right, is equal to K Q2 distance divided by R2 square. So K is same. So Q1 is 40 micron negative 6. R1, so what is R1? R1 is the distance of point P from charge number 1, which is, we call it x, and we are solving for x square. Q2 is 20 micron divided by, so R2 is the distance of charge number 2 from point P, which is 0.3 minus x, and there's a square, and negative 6, this cancellation, right? So then you do this cross multiplication and then solve this algebra. So it's gonna be 40, 0.3 minus x is 20, x is square, right? And then you do some 40, 0.3 square minus 6x plus, I'm just doing algebra, minus 20x square is equal to 0. And after playing with this algebra, you will end up with some quadratic equation, and solve this quadratic equation. So I will leave it with you. So you will end up with some quadratic equation. So solve the quadratic equation, and quadratic equation will give you two solutions, right? It has two roots. So x will be either, so if you want to solve that, I have the answer, either 1.02 meters in meters, or 0.176 meter, which is 17.6 centimeter. This is 102 centimeter. Okay, but you can have only one solution, right? So then you go back to the picture and pick the one which makes sense, right? Since the distance between these two charges are 30 centimeter, right? This x cannot be greater than 30 centimeters. So then this is not possible. So your answer is this. So your x is 17.6 centimeter. So that particular point where the net electric field is 0 lies at x is 17.6 centimeter from the first charge, right? Okay, so that's part A. Now part B is just conceptual. It says it is not possible to find any point left of this, right, where or right of this along the line joining the two, where the net electric field is 0. Why? To answer this, draw the electric field vector. So it's simply asking, let me draw the same picture. You have 40 microcoulomb, and the second charge is 20 microcoulomb. It's just action. Let's draw the axis. This is the x-axis. It's action here. Net electric field not equal to 0. Here in the vicinity here, the other side also, you cannot find any point where net electric field is not 0. Both ways. Why? Then let's figure that out. Why? Because if you pick any point near here, right? So what's the electric? This is charge number 1. So electric field due to the point number 1 is that way, and electric field due to point number 2 at the same point is also same direction. So they will not cancel out. The net electric field is that way, right? Same here. If you pick any point here, right, and try to find the electric field. So electric field due to charge number 1 is that way. It will be weaker, and the electric field due to point number 2, charge number 2, will be stronger because it's close to this E2. But still, they will not cancel. The net electric field will be that way, right? So you cannot find any point here or here where net electric field is 0, and this diagram obviously illustrates that, right? So here's the next problem. So it's a very general, typical question in electrostatics. So it says a charged sphere, this is a charged sphere, charged particle, is suspended with the help of insulating thread, in an electric field. So you have electric field here, uniform electric field in this direction. Right? This is the electric field, and this electric field, you can imagine, is produced by two metal plates. It's called capacitor. So positive side is this side, let's say, right? Just imagine. You don't need to show that, but if you want to produce electric field in this direction, right? So this is how you produce the electric field, as I explained in my lecture slide actually. So this is how. So here you do this experiment like in between the two big plates. One is positive, one is negative. So the electric field. So you suspend a charged sphere whose mass is 3.2 gram, and it says actually the charged particle deflects against the electric field, opposite to the electric field. It's making actually 37 degree with the vertical as shown. The magnitude of the charge here, right? This magnitude charge is 10 microcoulombs, right? And based on this information, so it's asking these questions. So first of all, draw the free body diagram showing all the forces acting. So let's draw the free body diagram here. So first of all, since it has a mass, it has force of gravity, right, mg, which is really small actually compared to the electrical force. And you have tension force going this direction, T, right? Tension is keeping it from flying off this side. And you have the electrical force, electrostatic force going this direction, right? That's the reason actually it's going that way, because right, the electric field deflects actually that way. That means electrical force is that way. So, and what's the magnitude of that in terms of electric field? So Q times C, that's the electrical force. Q times C, right? So that's the free body diagram. So that's done. So the second part is the charge on the sphere must be positive or negative charge. So what do you think? Is this hanging charge is positively charged or negatively charged? So based on this, it must be a negative charge. Why? Because the reason is it deflects. It is deflecting, right? It deflects opposite to the field, electric field. That's why. That's the reason. Because electric field is to the positive side, its deflection that way. That means it must be a negative charge, right? And the next question is now balancing the y component of the tension force, calculate the tension in the string. Okay, tension in this. So back to the problem. So let me draw the free body diagram again. Tension force, right? And this is mg, and this is your electrical force Fe, which is QE, right? And but tension is making some angle, and it gives you the angle 37 degree with the vertical, not with the horizontal. And since this is 30 degree, you can do trigonometry. So this is the y component, which is, and if you do trigonometry, it's gonna be t cos 37 degree, not sine, cos, because if you do trigonometry. And the x component is t sine 37 degree if you do trigonometry. Now it says balance the y component, right? Because everything is in static equilibrium. Ax is 0, ay is 0. There is no acceleration. So now balance the y component of the force, right? Because there's no net force acting on, so it must be 0. So what is the net force? What is the net force along the y-axis? So t cos 37 degree minus mg is equal to 0. Now it's actually calculate the tension. Tension is mg over cos 37 degree, right? So mass is given 3.2 gram, right? But gram must be in kilograms. 3.2 10 to the power negative 3, 9.8 cos 37 degree. If you do that, so you'll get 0.039 newtons. Okay. So next question is now balance the x component of the tension force, then calculate the electric. So we are going to do the Newton's second law in x direction. It has to be 0. What's the net force in x? So t sine 37 degree, right? This is counterbalanced by the electrical force, which is QE, right? Because it's going opposite direction. Has to be equal to 0. And now we already know tension from here. It's acting. What's the electric field? So this whole thing is actually Fe. Let's call F of E, electrostatic force. So electrostatic force is simply T sine 37. It's 0.039 is the tension of sine of 37. So the electrostatic force acting on this charged sphere is 0.024 newtons. Next, now is find the magnitude of the electric field. Now we already got the electrical force, right? And it's acting, what's the magnitude of the electric field E. So electric force is Q times E, right? So electric field magnitude, right, is given by this force, whatever force, divided by Q. So force is 0.024, and the charge of this hanging mass is 10 microcoulomb. Micro means this. So this is the electric field magnitude. Okay, and if you do that, 2363 newtons per coulomb should be the answer. Okay, that's how you solve problems like this. So here's the next problem. So it's asking you to find the net electric field at point A, due to these three static charges. So placed at the corner of this rectangle, So this charges, let's say this is charge number 1, charge number 2, charge number 3. This is positive 10 nanocoulomb, negative 10 nanocoulomb, and 5 positive 5 nanocoulombs. So, and these are the distances. And this is the empty space. This is the test point. So it's asking what's the net electric field at point A, empty space A, due to these three charges, right? And just follow the rules, so just follow the rules. So first, based on the rule, first you need to draw the electric field vectors, right, due to individual charges. So due to charge number 1, right, which is positive charge, what's the electric field at point A? So since this is positive charge, the electric field at point A will be like this. This is E1 away. Point number 2, similarly, what's the direction of the electric field due to charge number 2 at point A? So this is diagonally, it has to be diagonally, right? And since this is a negative charge, it has to be towards the charge. Remember, this is your E2. And again, charge number 3 is positive. So what's the direction of the electric field at point A due to charge number 3? Again, this is positive charge, it has to be away from the charge. So these are the electric field, individual electric fields, due to 3 different charges. Now the problem is to find the net electric field, so which is then just the vector sum of E1, E2 and E3. You just need to do the vector sum. So to do the vector sum, you might need this angle, right? And so this is 2 centimeter, 2 centimeter. So this theta is from trigonometry inverse tan 1 divided by 2, right, half. So that theta will be 26.6 degree. First find that out. And then so first remember the rules are the recipe is our recipe to solve the electric field problem is first draw a clear free body diagram for each electric fields. Second part is find the each magnitudes using the formula. So E1, right, is the electric field at this distance, 2 centimeter distance to the first charge, is KQ1 magnitude R1 square. So K is 9 10 to the power 9. Q1 is 10 nanocoulombs magnitude, negative 9, divided by R1 is 2 centimeter. But make sure you convert into meters, right? Because all the constants are in this constant is given in standard unit. So that's it. So E1 magnitude is 225,000 newtons per coulomb. Similarly, E2, right? But to find the E2 first, to find the electric field due to point number 2, charge number 2, negative charge at point A, first you need this distance, the diagonal distance, and that this diagonal distance, right, will be 1 square plus 2 square. So that's going to be 2.247, Pythagorean theorem. So similar, E2 magnitude is KQ2 R2 square, 9 10 to the power 9. Q2 is remember, even if this is negative charge, you just need the magnitude, okay, because this electric field formula can only calculate the magnitude. So distance, this point is at distance 2.24 centimeter from the second charge, so 0.0224 square. So E2 magnitude is, if you do 179,368 newtons per coulombs. And one more, E3 magnitude, which is this, is KQ3 over R3 square. So 9 to the power 9, Q3 is 5 nanocoulombs, negative 9, divided by this distance is 1 centimeter, 0.01 square. Okay, and if you do this calculation, the magnitude E3 is going to 45.3 newtons per coulomb. Okay, so we have found all the individual magnitudes of the electric field. Now do the vector summation. So what do you need to do? So the vector summation would be, first we need the sum of the x component of the electric field, right? So sum all the x components. So it has two components. This electric field, right, has two components. The E2 has one is so E1. So in x, you are summing all the x components. So E1 is positive, but this E2 is going to the component. This is in second quadrant. So E2 cos theta is 26.6 degree, right? And that's it, right? The E3 has no x component. That's it. So E1 magnitude 225,000 minus E2 magnitude 179,368 cos of 26.6 degree. So that's the sum of x. And if you do that, It's going to give you 64617 newtons per coulomb. Okay, that's the sum of the x component. So similarly, you're going to need sum of the y component of electric field. So y component is, let's see here, you have the y component of E2 is, right, in second quadrant is positive E2 sine, right, sine 26.6 degree, right, because it's up, the y component is up, see, right, but it is balanced by, right, E3 is going down, so it's so that's gonna give you the sum of the y component, right, and put all the numbers. So E2 magnitude is 179368, sine of 26.6 degree, minus E3 is 450000. So that's gonna get you sum of the y component, right? And that's gonna give you the sum of the y component, negative 369686. See, this came out negative. So that's all you need, right? And next is now finding the net electric field, the magnitude of the net electric field. Then now we're almost done. Sum of x component square plus from Pythagorean theorem, sum of y square, right, square root. This 64167 square plus 369686 square root. So the net electric field at point A, right, that empty space A, due to the three charges, is given by this. So the net electric field is 3.75. So double check this calculation, 10 to the power 5 newtons per coulomb. So that's the net electric field at this point. But what's the direction of this field? Because it's a vector quantity, right? It's a vector quantity. So theta r is the angle made by this net electric field with the x direction, is inverse tan sum of the y, sum of the x. Just put the magnitude. Sum of the y is 369686 divided by sum of the x is 64617. So theta r, if you do that, is 80.1 degree. And what's the quadrant, right? You have to mention the quadrant. So is this, then to mention the quadrant, you have to see the components. Sum of the x component has positive, right? Sum of the y component is negative. So that means if you check the quadrant, this all positive, right? Negative, positive, negative, negative, and positive, negative. So you have to see this first, second, third, fourth. So let's see. You have x component is positive and y component is negative. So that means it lies in fourth quadrant. In the fourth quadrant, right? So that means the net electric field makes almost 90 degrees, so 80 degree, right? So if you want to draw, so this is the theta r we have just found, right? This is the x-axis, y-axis. So this is the net electric field, which you're going to use next part, okay? So this is just the continuation of the same problem 6. Now this is the part B. Now it says if a small positive test charge, right, positive charge of mass this with a charge this is placed at point A, draw the force it experiences. So remember you had a square, right, and like this point A was this, right? You have positive charge, negative charge, positive charge, right? And we from part A we just found, if you check the part A, the net electric field, right, net electric field vector was making theta r is 80.1 degree in fourth quadrant. So that was the net electric field we just found. Now it says now put up small test charge, right? This is the test charge, small test charge whose magnitude is charge is 4.8 10 to the power negative 19 coulomb. Its mass is 1.2 10 to the power negative 21 k. Then it says What's the force, both magnitude and direction? Force acting on this charge due to this electric field. Now it's easy. The force on this test charge is just Q times C, E net, right? The net force on any test charge is, if you already know the electric field, just Q times C. So Q is 4.8 10 to the power negative 19. Net electric field is from the part A, which is 3.75 10 to the power 5th newtons per meter. This is from part A. Okay, that's it. So that's the net electric field experienced by this small positive test charge placed, right? And if you do this calculation, so you can do this calculation. 3.75 exponent, right? So it's going to give you 1.8 to the power negative 13 newtons. And in which direction? So since it is a positive charge, in the direction of E, the net electric. Why? Because it's a positive charge, right? So the force will also be in the same direction as the electric field. If it were a negative charge, it would be opposite direction. Okay, so we found the force. So next, find the acceleration produced. Now it's easy because we already know the force. Mass is given. So from Newton's second law, right? Newton's second law says mass times acceleration, right? So acceleration is net force acting on any object divided by mass. So net force we have just found, divided by mass of that test charge is given. So that's the acceleration, right? And it experiences very high acceleration, and that's not surprising because this test charge's mass is very small. And again, its direction is in the direction of the net field, F net, right, and E net, because they are at the same direction. So acceleration must be in the same direction as the net force, right, from Newton's second law. Here's the next question, and this is the dynamics of the charged particle in electric field. So it shows how charged particle behaves in electric field. So here's the problem: a negatively charged particle, right, is shot in between the capacitor plate, right, so it deflects, right? It is deflected by the electric field, right? Because why? Because electric field exerts force and it deflects, and it takes the parabolic path trajectory. And this is similar to projectile motion. Actually, you can think about projectile motion is nothing, it's just the motion of the mass in gravitational field, right? If you shoot something, right, some mass off the table, right, it takes a parabolic path like this. You can do many dynamics, kinematic equations, right? This is just like that. So instead of so you have gravitational field, right? Now you have electric field. That's it. But in electric field, you could have positive charge or negative charge. Unlike mass is always positive. Okay, so here's the first question. So it says the electric field is provided by this capacitor plate, which is given by this, and this negatively charged particle is shot at this speed, right, very high speed. Its mass is given, and the charge, this charge is of 10 microcoulomb. So here's the first question: calculate the force on the charged particle in x and y direction as it enters the electric field, right? So here's both the x and y component force. So x force is Q times Ex, and which is 0. Why? Because there's no electric field in x direction. As you can see, the electric field is, the uniform electric field is all vertical, right? Vertical. There's no electric field in x direction. However, y electric field is Q E Y, right? And it's Q is the charge of the test charge particle, 10 microcoulombs. Electric field is 10,000, right? And its direction is up. So 0.1 newtons positive, remember. right? That's the reason actually, is because since it's a negative charge, but electric field is down, right? So the negative charge would feel a force in opposite direction. So the force here at any point is that way, a constant force. That's the reason it's been deflected upward. So that's the force, Fy. Okay, so it's in upward direction. So that's it. That's the answer. So next part is calculate the accelerations in both x and y directions. Since masses are given, now it's not a big deal. So acceleration in x direction is force in x direction divided by mass. This is 0, of course. Ay is now Fy over mass. So 0.1, the mass is given 1.5 10 to the power negative 15 kilogram. That small bit of charged particle shot has a mass of that. And that should give you 6.67 10 to the power 13 meters per second square. So again, in upward, its direction is upward direction because it's a vector quantity. Okay, so now next part is just the continuation of the same problem number 7. How much time it takes to exit the plate? Remember, so go back to the question, right? It says, so it enters here and exit here, so it says how much time it takes. So you just need to use kinematic equation. Remember, x and y motions are completely independent, so you have to use one of the kinematic in 2D motion. Remember, x and y components, right? You can treat them completely independent. Okay. You can use x motion. So when you use x motion, just completely ignore y. When you use y motion, completely ignore x motions. So since the length is length given, no, the velocity is given, right? So then let's see, is it missing something? So this length, I forgot to mention here, the length of the plate is 2 millimeter. Okay. So that's somewhere I forgot. But then x motion, you have to use kinematics in x direction. So x is x naught, if you remove the kinematics formula, right? V naught xt plus 1/2 axt square. But in just like projectile motion, the x acceleration is 0. This x is 2 millimeter. Millimeter means this is -3. This is 0. Starting point is 0. Plus initial velocity is given. So initial velocity is 2 10 to the power 5. It was shot with that much initial velocity, and it deflects like this. And this is 2 millimeter. Right, and times t, and then t is 2 millimeter divided by 2 10 to the power 5th, and that's the time it takes, 1 10 to the power -8 seconds. So it's about 10 nanoseconds, right? In nanoseconds, and that's the usual time for charged particle. It takes very little time because it has very high acceleration. Okay, so it takes about 10 nanoseconds to cross the field. Okay, so now next part is, here's the next part, right? What is the angle of deflection as it exits the field? So it's asking what's the angle it makes, right? The final velocity, this is the final velocity, say, right? What's the angle of deflection, right? So then you're going to need the final velocity. So both the x and y components. So final velocity in x direction is final initial velocity plus axt. This is one of the kinematics. Again, ax is 0. So the x component of the velocity doesn't change, right? Because there's no acceleration in x direction, obviously. So it remains same, 10 to the power 5th. meters per second. What about the final velocity in y direction? And which, however, does change because it has acceleration in y direction, right? So it does change. So then just use the formula. Since we already know the time will be same, right? Time is scalar quantity, time will be, we have already found the time. But this is 0. Why? V naught y is 0 because initially there's no component of initial velocity in y direction. So this is 0, right? The initial y component of the velocity is 0. And ay is from part B. Part B acceleration is 6 point, is the 6, 7, 10 to the power 13, right? And time is 10 nanoseconds, so 1 10 to the power -8. So that's the final velocity in y direction, y component of the final velocity. And 6.67. Okay. Okay, so now you got final x component of final. So then from this, right, you can find the, this is what we found, right? X component of the final velocity, y component of final velocity. So then from vector, then the angle of deflection is just tan inverse y component, x component, right, from trigonometry, divided by x component is same. So that's, it makes 73.3 degree. When it exits the field, right, it is deflected by 73 degree. So that's how you solve. So this is nothing, it's just a project solving like a projectile motion problem using dynamics and kinematics, just a reminder.